Hi everyone, we're going to look today at question 11 from exercise 5E, so we'll get straight into it. In terms of the first bit, what we have to do is find the value of K using the temperature and the time. So let's do it. So part there, obviously the temperature is going to be equal to 20, so 20 is equal to 5 plus 95. E to the minus k times by 15. So bring the 5 across, that makes it 15. We can also bring the, in a second we'll bring the 95 down, so it's minus 15k, so therefore 15 over 95 is equal to e to the minus 15k. Take the ln of both sides, ln of 15 on 95 is equal to minus 15k, so therefore k is equal to ln of 15 on 95 all divided by minus 15. So when we go to our calculator, we do that on our calculator, so I've actually already done that, and we get an answer of 1.23. So if we put that back into there, equals 0.123. We can then write our model as t to the t is equal to 5 plus 95 e to the minus 0.123t. So that's the model that we have to use for the rest of the question. The question says then, part B, what is the temperature of the liquid when it's first placed in the refrigerator? Obviously T will be equal to 0 then, so T of 0 is equal to 5 plus 95. Now that will turn out to be e to the 0, which we know is 1. 5 plus 95 is 100 degrees C. The next bit is to show that the rate of change is directly proportional to T take 5. Now if we do this, so the derivative of that is t, so the 5 goes out, then we're left with 95 e to the minus 0.123t, which we know then we have to actually work out the integral, the differentiation of the power, which is minus 0.123. We could say that particular model, if we wanted to, is simply proportional to some constant k. The k value would be 95 times by that value there, and the model bit, which is really important, is the e bit 123t. Now if we also compare that to what we have up here, t take 5, that would be equal to 95 e to the minus 0.123t, which we could say is t take 5 is directly proportional to some value k e to the minus 0.123t. So in this particular case, therefore those two things are equal. T is directly proportional then to t take 5. Right. The next part of the question asks us to find the rate of change of that at various times. Now obviously we could put into the original question, so we've got our model, that works out to be, if we actually rewrite that as t dashed is equal to, when you times the 0.123 negative with the 95, you get negative 11.685 e to the negative 0.123t. So all you're really asking me to do for that, when you start putting in t dashed of 0, you're putting it into the equation. A better way of doing that is to actually go to your calculator, go into your function, put that particular model into your function and graph it, and then go to your calc go down to number 6, and you can put in the value of 0. Alright, so 0 will tell you what your rate of change is. So there it's actually negative. So it's negative 11.685, and that would be degrees C per, and I think we're looking at per minute. Right, the next one we have to actually do is looking at the temperature of 10. Can't write. That's equal to, and I go back to my calculator again, and then all I have to do is second function calc, put in number 6 and put in 10, and it will actually work out my rate of change for me. Negative 3.42, negative 3.42 degrees C per minute, and then the last one I need to do is 20. Going through there, number 6, and put in 20, and it will work that out for me. So that's negative 0.998. degrees C per minute. Alright, thanks for listening. If you have any troubles with that, make sure you catch up with me in class tomorrow. Bye.